Hello everyone. So first, thank you for coming to this celebration of Emmanuel's works. So I'm going to be very, it will not be a scientific talk. I will just give a few stories about some of these papers. So first, most of Emmanuel's work, so Bertrand was talking about trees, but more generally it's about graphs, many kinds of graphs, graphs with colors, graphs with cycles, graph meanders, and let's meander around all that, okay? See if we can close the cycle in the end. So first, so one of the first works we did with Emmanuel and Philippe was this paper that Philippe already mentioned, coloring random triangulations. Let me tell a little bit of story about that paper. The story is that it was at the same time a failure, but which became a success, and in fact a much bigger success than we expected at the beginning. So in fact, I was also returning from my VSN, military service, and I had not done, nearly not done any math or physics for 2 years. I was looking for a subject related to random matrices, quantum gravity, and you know, Philippe and Emmanuel, they started to work because they were sharing an office. But in fact, many of the works done probably in every labs in the world is done starts very often in the coffee room. And in the coffee room, they were always talking about meanders, timbre. And I started to think, oh, there is a matrix model to do that, and let's solve that matrix model. And I thought this matrix model was solvable. And we started working on this matrix model. Let me write a matrix model. So this is the one which is in the paper. It's not the meander matrix model. The meander matrix model is slightly more complicated. And in fact, somehow, I must recognize I had made a mistake, and I thought the meander matrix model was solved. It was not. But as a byproduct, we realized that we could solve that one. And that one is a kind of, it's not a meander problem, but it's another problem, and we try to see what is it counting. So it's a two matrix model. You have two matrices. So let's say two kinds of vertices, black and white. Okay, and there is a AB in the exponential, which means that you should connect A and B, so black and white. So there are edges black and white, and there is these potential terms that mean that you can have vertices in A of any degree, vertices in B of any degree. And indeed, one of the skills, combinatorial skills of Emmanuel was to recognize that if you now put, so this gives that, so this model counts this kind of graphs. But now the nice thing is that if you insert a gray vertex in the middle of each face, you see that you have a triangulation with every triangle having its three vertices of different colors. So it's the same problem. And basically in this paper, we solve this problem. We compute everything. And in particular, there is this formula, which is the one that Philippe already showed you before. And we ended up with this beautiful formula where U1 is basically a generating function counting trees associated to white, U2 to black, and U3 to gray. And this puzzled Emmanuel a lot. So I didn't know. For me, it was nice enough. I stopped there. This was the end of our paper. But for Emmanuel, it was the beginning of the story, because Emmanuel started to think, why can this be described in terms of trees, of three types of trees? Why this formula? And that's how he started to investigate about Gilles Schaeffer bijection. And this led to the famous Boutier-Di Francesco Gitter bijection in the end. So this was in fact the beginning. So that's why I say he started from failing to solve the meander problem, but succeeding in solving the three colorable triangle problem. And in fact, it started all this bijection story. So it was really a great success, I think. Okay. Let me go so the next thing is the paper we did with Charlotte Christiansen about Hamiltonian cycles. So which Philippe mentioned. I don't have any particular story about that paper. It was a nice paper. It was really enjoyable to work on that, and we just solved. We found the critical exponent. Well, I mean, it was a straightforward application of the random matrix method that we had developed with Charlotte on the ON model. It was more or less a straightforward application, but it was fun, and it was a nice result. And the Hamiltonian cycle, by the way, is a cycle that goes through all vertices only once. So it's a unique cycle that goes through all the vertices. And you want to count how many such cycles can be on a random triangulation, for example. So we just solved the problem. Now the next paper is a recent paper, so it was just last year. And it's related to this to the counting of mobiles. So this, I think you will see this kind of picture in the talk by Jeremy, but these are the mobiles that are behind the famous Boutier differential unitary bijection. And basically they can encode many sorts of maps, hypermaps, constellations. It's a very, very general model, and that's why this bijection is so fantastic. And typically what people would like to be able to compute are the generic functions. Let's say this generic function Ri, which counts mobiles with a label vertices at height with label I. So, and in fact, Philippe, Emmanuel, and Jeremy had made a guess. I mean, they had tried a lot. They have done a lot of computations on the computers, and they had a guess for this function. And it's a very explicit formula involving a ratio of determinants, very, very explicit. But and they even managed to prove it for some cases, but mostly it was a conjecture. And again, this happened in the coffee room. We discussed that in the coffee room, and I was there, and I listened to them, and I say, oh, but I recognize this determinantal formula. It's a determinantal formula typical of integrable systems. It's a Krichever formula. And so I said, oh, it must be easy to prove, and we started to work on that with Michel Berger. And this was more than 10 years ago. And we started to announce, oh, we know how to prove. And we were able to prove that, indeed, the formula satisfies the recursion equation. But we had forgotten a little detail. It's the initial condition. And in fact, it's exactly the case where, in fact, Krichever formula is not applicable, or at least it's a degenerate case of Krichever formula, and it had never been proved that Krichever formula survives the degenerate limit. So we had to somehow reinvent a proof in that case, and we had so it was a bit more complicated. But and we finished with Soufiane, my student Soufiane Oukassi, and who played a very important role in the process. And I think Emmanuel had a lot of fun working with him, but eventually this is the formula. So Rn is a ratio of 4 determinants, very explicit. In fact, in the process, we also get, Q is W and P is B, but we also get explicit formulas for all these generic functions. And basically now, problem solved, and the paper now exists, and is even accepted in the journal. So now this is a theorem which had long been awaited by the community. And very often people like Gilles or other people ask me, so have you proved the conjecture? Is it published? Okay, now it is. Okay, thank you for attention. And I want to say thank you to Emmanuel. It was really great pleasure to do all these works. And indeed, Emmanuel is very good at guessing bijections and all that. And thanks a lot to everyone. Okay.